All right, this is MA 161's Exam 2 from looks like spring 2020. And look at that date there. That is like 1 week before all of the like the COVID shutdowns and stuff. I think Purdue campus did theirs on I think March 12th. So this is about 1 week before all that. So that's kind of interesting how this exam was given and designed right before all the crazy times. So that's fun. Going on to the first question, just a limit, but it's a bit different. It's the limit as x approaches infinity. So that's weird. Usually it's, x approaches a composite number like 2 or 0 or something. But this is actually a good thing. Limits as x approach infinity are usually easier because you've got a lot of flexibility in how you can actually calculate the limit. What I mean by that is because the limit is approaching such a large number, it's approaching infinity, constants like this plus 1 here, they don't really change anything in the grand scheme of things. All this plus 1 is going to do is probably just like move it up 1 unit or right 1 unit or something like that. But as x grows larger and larger without bounds, it starts to become not relevant at all, and you can just basically just forget about it. Now, I wouldn't say the same thing about this 2 minus and this 2 here. Oh, actually, yes, you can, because if we were to just multiply this denominator out, we'd get 4 minus x squared, and you can do the same thing here. You can basically forget about the 4, and we're just left with 2x squared over negative x squared. And now here, you can see you can just simplify. These x squareds cancel out, and you're left with negative 2, and we already have our answer. So now you see what I mean by these limits as x approaches infinity questions. They're usually pretty flexible with how you can find the answer here. Question 2, we have another limit here. This time as x approaches negative infinity. And just like problem 1, where x approached positive infinity, that's a really good thing because it means we have a lot of flexibility and a lot of things we can do to this limit here to make it a lot simpler to find the answer. And the big one is these added constants here, this plus 1 and this plus 5. Now, in the grand scheme of things, as x approaches larger and larger numbers, these added constants aren't really going to do anything. Like in a case, if this limit was x approaches like 1, that would make this 1 plus 1 equals 2, and 1 plus 1 equals, or 1 plus 5 equals 6. And those differences are a lot bigger compared to like if x was approaching 1,000,000. That would just be 1,000,001 and 1,000,005. So as x gets larger and larger, these added constants become more and more meaningless. So as x approaches infinity, they become totally meaningless, and we can basically forget about them. So we're left with a much simpler problem to simplify this square root of 9x squared all over x. And doing that, let's see, square rooting the top, we get 3x. That's all over x, and when you cancel the x's out, you're left with 3. Now, that's close to the right answer, but it isn't necessarily the answer. Like, that's not necessarily the answer, because when you do these tricks, sometimes your sign gets flipped. Sometimes you're left with a positive answer when it should be negative, and vice versa. So we know the answer is either C or D, so we're 50-50 with that. But let's go ahead and figure out which sign it actually should be. So to do that, we can just imagine plugging in a very large negative number into both the numerator and the denominator and see what signs we get on both the top and the bottom. So on the top, if we were to plug in negative infinity in for that x there, this squared there is going to make it positive. And this multiplied by 9 in the square root isn't going to change that. So on our numerator, we're going to have a positive top there. And on the bottom, it's just x. So as x approaches negative infinity, the numerator is going to be negative. And a positive divided by a negative equals a negative. So we know that our answer is going to be negative 3. Question 3. It's one of these piecewise questions. I kind of like doing piecewise stuff. So it's defined as x minus 5 whenever x is less than 2. It's defined as 5x minus 13 whenever x is greater than 2. And when x equals 2, it's just defined as -5. So that's the piecewise function. Now it's asking, why isn't it continuous at x equals 2? Which one of these 5 reasons is the case for the function not being continuous at x equals 2? All right, let's go through each one of these one by one. Starting with A, g of 2 is not defined. That is wrong because it is defined. G of 2 looks like it's going to use this definition here because x equals 2, and g of 2 equals -5. So, yep, it's defined. That one's not right. What about B? The limit as x approaches 2 does not exist. Okay, so for the general limit, aka the not one-sided limit to exist, both the left-sided limit and the right-sided limit have to approach the same value. And how we could find that out is just plugging in x equals 2 into these outside functions there. Because since they aren't defined at x equals 2, which is the value that we're approaching, if we get the same answer for plugging in x equals 2 in for both these definitions, then the general limit will exist. So if we're going to do that, we'll get, so x minus 5, you plug in 2, you get 2 minus 5, which equals -3. And for 5x minus 13, you plug in 2, you get 5 times 2 minus 13, which equals also -3. So that's great. We have the same value here. So that means that the limit as x approaches 2 does exist, and it equals -3. So B is wrong. Now what about C? The limit as x approaches 2 does not equal g of 2. Okay, well, we just found the limit as x approaches 2. We said it was -3, and g of 2 equals -5. Hey, that's actually true. This one, this C here is, it's correct. That probably means that it's the right answer, but just to be safe, let's go ahead and go through D and E and make sure that both of those are false as well. So looking at D, g of 2 does not equal -5. Yes, it does. G of 2 equals -5. So D is wrong. And now just looking at E, there's a vertical asymptote at x equals 2. That's not what asymptotes mean. Usually asymptotes are created because you have some function that goes like this, where x approaches, or x like borders on an imaginary line there and then picks back up at the same spot where it kind of approaches infinity at that point, and you have this line that it never crosses. That's an asymptote. What we have here is 3 function definitions where the outside ones are approaching the same value, but that value is defined at a different point. That's what happens if you graph out this function. It's going to kind of look like that. And that's not an asymptote here. That's just a discontinuity, a jump discontinuity. So because of that, E is false, and we know that C is our right answer. Question 4. Okay, so this just kind of looks like a derivative where we have f of x equals 2x squared plus 4. And looks like it wants us to find its derivative and then plug in 3. So, well, it actually wants us to do it a little bit differently. It looks like it doesn't really want us to solve it all the way through and get a specific answer, a specific output. Kind of just wants us to set it up using one of the kind of limit properties we can use to evaluate derivatives. There's 2 main ones. The one that I remember the most was this, the limit definition of the derivative, where you had, f of x plus h minus f of x all over h, that thing. I think you could use that, but for whatever reason, the answer, so spoiler alert, the answer actually isn't any of these. It doesn't use the limit definition of the derivative at all. I don't know why. That seems like the most reasonable answer you could get for this, but whatever. So it's going to be either B or D, and for both of these, it kind of just looks like they use the old slope formula that you learned back in like an algebra class, where you had y2 minus y1 over x2 minus x1. That's how you find like slopes. If you have 2 pairs of points, you can find the slope of the line that intersects them. So we could just use that and retrofit it with some things from the problem statement, and we can get our answer that way. So what I mean by that and how we're going to set this up is we're going to do limit as x approaches, looks like, so it's going to be limit as x approaches a. Sorry, I want to show like the general variant of how you'd set this up, and then we can actually go in and plug in, these values after that. So this is going to be limit as x approaches a of f of x minus f of a all over x minus a, where a is the value that you're evaluating this at. So plugging everything in for this, we get limit as x approaches, so in this case it's 3 of f of x, so that's just going to be 2x squared plus 4, 2x squared plus 4, minus f of a, so the same thing, but we just substitute x for a, and a is 3, so we just substitute x for 3, so it's going to be 2 times 3 squared plus 4. And then on the bottom, we still have our x minus a, which is 3. So now that we have this set up, we can just go ahead and simplify this fractional part, and we should get our answer from that, assuming we did everything correctly. So this is going to be the limit as x approaches 3 of 2x squared plus 4 minus 3 squared is 9. 9 times 2 is 18. 18 plus 4 is 22, so minus 22 all over x minus 3, which evaluates to, so plus 4 and minus 22 is minus 18, so 2x squared minus 18 all over x minus 3, and B is our answer. So I have, to be honest, I have no idea why it's not A. If you were to evaluate this using this, the limit definition of the derivative, you would get A. And I actually already recorded this question and thought it was A. And I was super frustrated when I went back to the solutions, the answers page, and it was actually B. I was like, what the heck? So I went and talked to Dr. Chen about this problem and figured out you're supposed to do something differently. So thank God for him. But yeah, so just the slope formula, plug in f of x's and a's, and you should get your answer. Question 5, a derivative problem. We have our f of x, which equals 10 times the cubed root of x to the 4th plus x. We have to find this derivative and then plug in 8. So finding f of x's derivative, it becomes easier to do that once we rewrite f of x as 10 times x to the 4/3 power. We get this 4 from the x to the 4th and this 3 from the cubed root. And then this is all plus x as well. Taking the derivative now, that's a lot easier because we can just do power rule. We move that 4/3 out to the front, so this becomes 40/3 times x to the, so this would be 4/3 minus 1 is 1/3, so this would be x to the 1/3 power, plus the derivative of x is just going to be 1, because imagine there's a power of 1 there. If you move that out to the front, it becomes 1 times x to the 0th, which is just 1. So that's a plus 1. Evaluating this at 8 now, f prime of 8, we get 40/3 times, so this 1/3 power is the same as a cubed root. You know, what we did back at the start of the problem, we just kind of go in reverse. So this is going to be 40/3 times the cubed root of x, which is 8, plus 1. Evaluating all of this, that's a cubed root, not a square root. Simplifying, we get 40/3 times the cubed root of 8, that's going to be 2, because 2 times 2 times 2 equals 8. That is 3 2's, so 2 to the 3rd power. And then plus 1. One more step, we have 80/3 plus 1, which equals 80/3 plus 3/3, which equals 83/3. Question 6. At what points x comma y on the graph of f of x equals x over x plus 2 does the tangent line to f of x have a slope of a half? Okay, interesting problem setup, mostly because we're kind of going in the opposite direction of what we're usually asked. So normally for these derivative problems, you take the derivative of f of x and then plug in some x value, and then you try to find the slope, which is the answer. But in this case, it's the other way around. We're given the slope, and we have to find the x values that the slope occurs at. So to do that, I think we can just first find f prime of x, the derivative of f, and then set it equal to a half. And then at that point, we'll only have one variable, and we can solve for x. And then notice those will be our x values that these points lie at. So doing all that, first we have to find f prime of x, the derivative. So taking the derivative of x over x plus 2, we're going to need to use the quotient rule for that. So quotient rule is if you have a over b and you want to take its derivative, that's equal to a prime b minus ab prime all over b squared. So in this case, a is x and b is x plus 2. So just fitting both of those into our little formula here that'll give us our derivative. So doing this one step at a time, we get a prime, the derivative of x, which is just 1. B is x plus 2, minus a, which is x, times b prime, which is the derivative of x plus 2, that is also just going to be 1, all over b squared, which is x plus 2 squared. So now this all equals 1/2, and what I said earlier, we only have one variable in this equation, so we can just go ahead and solve for x, and that'll be half of our answer. And from there we can just figure out what the y coordinate is. So doing that, let's simplify. So this would become x plus 2 minus x all over, let's see, this will be x squared plus 2x plus another 2x, so 4x plus 4 equals a half. I'm running out of room here, but these x's would cancel out. We just got 2 on the top. At this point, we can probably cross multiply, where we multiply x squared plus 4x plus 4 times 1, which is just x squared plus 4x plus 4, and 2 and 2, which is 4. So now we're at this step. We can subtract 4 from both sides and get x squared plus 4x equals 0. We can take out an x from the left. We'll get x times x plus 4 equals 0. And then split this off into two separate equations. So we've got x equals 0 and x plus 4 equals 0. On the left, we've already got our answer, one of our answers, x equals 0. And on the right, we can just subtract 4 from both sides to get x equals -4. So those are our two x values. Based off of that, we can kind of already determine our answer because we've got a 0 and a -4 there. But just to be certain, we can go ahead and plug in 0 into our original equation, f of x, and see that we get 0 and 2 respectively. So doing that, we will get, so f of 0 equals 0 over 0 plus 2, which equals 0. That checks out. We are supposed to get a 0 there, and we did. And f of, this was -4, equals -4 over -4 plus 2. That equals -4 all over -2, which equals +2, and that also checks out. We have a 2 there, so we know that C is our right answer. All right, question 7. Oh, halfway point, just realized, that's cool. This is a derivative problem. A double derivative problem this time. We have to find f double prime of f of x. So this is x times sine of x. We need to do two derivatives on it. So starting with the first one, f prime of x, that is going to require the use of the product rule. So the product rule is if you have something in the form of a times b, you don't want to take its derivative, that's equal to a prime b plus ab prime, or in this case a is x and b is sine of x, so we can just fit both of those into this formula and we'll have our first derivative. So doing that, we get a prime, which is the derivative of x, that is just 1. B is sine of x, plus a, which is x, times b prime, so the derivative of sine of x is cosine of x. So we're in this state now. I'm going to simplify a little bit just so it makes it easier to do our next derivative after that. So this is now going to be sine of x plus x cosine x. That is still f prime of x, and now to find f double prime of x, we do another derivative on sine of x plus x times cosine of x. So derivative of sine of x is cosine of x plus the derivative of x times cosine of x. That's going to require another use of the product rule, where in this case a is x and b is cosine of x. So doing that, we get derivative. So we get a prime, which is the derivative of x, which is 1, times b, which is cosine of x, plus a, which is x, times the derivative of b. So the derivative of cosine x is negative sine x. That's weird looking. Sine x. There we go. So we're in this state now. Now we can just go ahead and plug in pi for all these x's, and we should get our answer. So f double prime of pi equals cosine of pi plus 1 times, which is nothing, so plus another cosine of pi plus pi times negative sine of pi. Let's evaluate all these trig functions. So cosine of pi, that is negative 1. So is this one. So minus 1 plus pi times, so negative sine of pi. Sine of pi is just 0. So this is all going to be 0. So we can basically forget about all of that. Negative 1 minus 1 is now negative 2. And that is our answer. Question 8, evaluating this limit here. This looks pretty nasty though. This tangent of, okay, that's tangent of pi times x. If that wasn't clear, which it isn't, so I don't blame you. All over x times secant of x. All right, that's a lot of trig functions. First off, what happens if we plug in x? So on the bottom, we're going to get, this is going to be 0 times secant of 0, which is equal to 0. And on the top, we'll get tangent of 0, which is also 0. So that didn't really work out. We didn't get a specific value. We have a divided by 0 here, so that didn't work out. But what we do know is that since we got 0 over 0, that's an indeterminate form. We have the option to do L'Hopital's rule if we want to. And I think we are going to, because I actually have no idea what other way to do this problem other than L'Hopital's rule. So L'Hopital's rule states that if you get 0 over 0, you can take the derivative of both the top and the bottom, and your limit will evaluate to the same value. So after you do those derivatives, you'll still get the same answer. So doing both of these limits, we'll get, so derivative of tangent of pi of x. So derivative of tangent, tangent x, taking its derivative, equals secant squared of x. That's kind of just something that you have to remember. You probably can figure it out by doing quotient rule, because tangent is just sine over cosine. So if you wanted to, you could evaluate that on your own with the quotient rule, but you could just remember that derivative of tangent x is just secant squared. So derivative of tangent pi of x is, so this is going to be the limit as x approaches 0 of secant squared of pi x, and then we do have to multiply by the derivative of the inside. We have to chain rule this. So the derivative of pi x is just going to be pi. And on the bottom, we're going to have the derivative of x times secant of x. That is going to make us use the product rule, which, again, I'm stating this product rule a lot because it comes up a lot. But anyways, a times b's derivative is a prime b plus ab prime. In this case, a is x and b is secant of x. So plugging in both of those into this formula that we've got on the bottom here, we'll get our derivative. So doing that, we'll get a prime, which is the derivative of x. That's going to be 1. Times b, that's secant of x, plus a, which is x, times b prime, the derivative of secant x. That, I think, is secant x times tan x. secant x times tan x. You could, again, if you didn't know what the derivative of secant x is, which I barely do anyways, you could just remember that secant x is equal to 1 over cosine x, and again, you could do the quotient rule to figure out what its derivative should be. But again, you could just remember that secant x is equal to. Actually, is it? Let me go ahead and check. Yes, it is. Okay, it is secant x. Yep, okay. Derivative of secant x equals secant x times tangent of x. So we know we're doing that right. So we now have our derivative, and now plugging in 0 in for all these x's should give us a valid answer. So let's go ahead and try that. On the top, we'll get, so secant squared is the same. I'm going to rewrite all of these secants as 1 over cosine. I do not like secants at all. I just like my sine, cos, and tan. That's all I can really work with. So I'm going to just rewrite everything in terms of those. So 1 over cosine squared times pi, times pi x times pi all over, so this is going to be 1 over cosine x for this, plus, this is going to be plus x times tangent of x all over cosine of x. I'm sorry, that's a really bad C. There we go. I tried to get away with it, but I couldn't. So there we go. Everything is in terms of sine, cos, and tan, which I find far easier to evaluate. So actually plugging in 0 now, we're going to get pi over, okay, pi times 0 is 0. Cosine of 0 is 1. 1 squared is also 1, so that's a 1 there. 1 over cosine of x, so cosine of x again is just, cosine of 0, I'm sorry, is just 1, so that's going to be 1 plus 1 times tangent of 0. Tangent of 0 is just 0, so it's a 0 times something, so this whole right side is just going to be 0. So we've got one more little step to do. We've just got, so on the top we got pi over 1, that is just pi, and on the bottom we also just have 1, so this is all just equal to pi. Question 9, a derivative problem, but we don't even have to plug in a value afterwards. So we have y equals square root of 3 minus 2x, and we need to find y prime, and that's just the same as a derivative. So rewriting this, y equals, what would be our best first step? I think it would be, so if we rewrite this as 3 minus 2x to the 1/2 power, that makes it clear that we can just do power rule, where we take the 1/2, move it out front, and then drop its power by 1. So doing that, we get y prime equals 1/2 times 3 minus 2x, all to the, so 1/2 minus 1 is -1/2. So we have the power there, and then we do have to abide by the chain rule. We have to multiply this by the derivative of the inside. So derivative of the inside, derivative of 3 minus 2x, that is just going to be, so the derivative of 3 is just 0, and the derivative of -2x is -2. So that is our derivative. Well, it looks like we have to rewrite it a little bit. It's not yet is it in the form of any of these answer choices. So we can go ahead and put this -1/2 power in the form of 1 over the square root of 3 minus 2x, like that. So this is going to be y prime equals 1 over 2. So this is how you account for that 1/2, 1 over 2, times the square root of 3 minus 2x. That's this. That's what we just set up there. And then all of this times -2, so -2 on the top. Looks like these two 2's are going to cancel out. We're just left with -1 on the top. And our answer should be, do we have an answer here? Oh, yep, we do. It's B. There we go. Awesome. Question 11. The slope of the tangent line to the curve described by the implicit function that at 2, 1 is what? So This is just a derivative problem, but it's a specific type of differentiation problem. It is implicit differentiation given away by that word there, as well as usually implicit differentiation problems also give you a pair of x and y values. So that's another giveaway that this is an implicit differentiation problem. And a third way of figuring out that that's what you want to do for this problem is your function that you're given. It's not simply in the form of y equals. It has a bunch of y's ingrained inside the function, and it would get really difficult to go ahead and separate those y's and get it all by itself. So instead of doing that, you can go ahead and do implicit differentiation, which avoids all of that. So implicit differentiation, what that is you basically just take the derivative of each term separately, and whenever you take the derivative of a y term, you multiply by dy over dx. So doing that, it's simpler than it sounds. Go ahead and doing that, where we have the derivative of y cubed x. That's going to require the use of the product rule. So the product rule is when you have a times b, and you take its derivative, that's equal to a prime b plus ab prime. In this case, a is y cubed and b is x. So fitting both of those to our formula here will give us our derivative there. So we'll now have, so a prime is the derivative of y cubed, that is 3y squared, and since we just took the derivative of something with a y in it, we are going to multiply this by dy over dx. So there we go. Now this is times b, which is x, plus a, which is y cubed, times b prime, which is derivative of x, that's just 1. Now, we just took the derivative of a variable, but since it was x, we do not multiply it by dy over dx. And now we have, that's this derivative done. Now we can go ahead and do this derivative here, y squared times x squared. That's going to require another use of the product rule. So now a is y squared and b is x squared. So doing that, we get a prime is the derivative of y squared, that is 2y. Multiply this by a dy over dx because we found the derivative of a y. B is x squared plus a, which is y squared, sorry. B prime is the derivative of x squared, that is 2x. And this is all equal to the derivative of 6, which is 0. So there is our derivative. Now we have introduced a third variable here, this dy over dx, but fortunately that's what we're going to solve for, and we're given the values of the other two variables, x and y. So if we go in and plug in 2 for x and 1 for y, and then solve for dy over dx, that'll be our answer. So you could either first get this entire function in a form of dy over dx, and that'll equal a big equation, and then you can go ahead and plug in 2 and 1 into that, or you can just start off by plugging in 2 and 1 into this equation and then solving for dy over dx. I think the latter way is much simpler to do, so we're going to go ahead and do that just now. So this is going to be 3 times 1 squared dy over dx. Again, this 1 is that 1. This is all times x, which is 2, plus y cubed, that's 1 cubed times 1, plus 2 times 1 dy over dx, times x squared, that is 2 squared, plus y squared, that's 1 squared, times 2 x, which is 2 times 2, that all equals 0. Now, we still have our dy over dx's hanging around, but we no longer have any other variables. So we can just go ahead and simplify and solve for dy over dx. So to do that, let's start by multiplying all these things out. This 3 times 1 squared is just 3, and this 2 is a 2. So this is going to be 6 times dy over dx. This plus 1 times 1 is just plus 1. This here is going to be 2 times 1 times 4, which is going to be 8 dy over dx. And then we have this term here, which is 1 times 2 times 2. That is going to be plus 4, all equals 0. Let's go ahead and combine like terms. So this 6 dy over dx plus 8 dy over dx equals 14 dy over dx. All plus 1 plus 4, which is 5, equals 0. Subtract 5 from both sides, we get 14 dy over dx equals negative 5. Divide by 14 on both sides gives us dy over dx equals negative 5 over 14, which is E. Question 12, the last question for this exam. How awesome. This is a derivative problem. We have our f of x here, and we need to find f prime of x and then plug in 1. Cool, we've done that before, but this one looks a little tougher. This has got a lot of things going on. It's got that natural log, fraction, some power components in it. We'll probably have to use a number of different rules to do this one. So I'll try to write smaller because this probably will run longer than the other ones, and hopefully we'll get the right answer at the end. We don't make any incidental slip-ups. So to start, I think we'd have to take the derivative of this natural log here, this ln. Fortunately, that's pretty easy to do. Derivatives of natural logs are just 1 over the inside. So we basically just take this fraction here and put it on the denominator of a 1 over x function there. And fortunately, since it is a fraction, we can basically just take the reciprocal of it. Since when you put a fraction in the bottom of another fraction, it basically just inverts it. It flips it around and you just take its reciprocal. So to start off this derivative, we're just going to do f prime of x equals the reciprocal of this fraction. So this is going to be x plus 1 to the 4th all over 3x minus 1 squared. I wish it was that simple, but we do have to do chain rule now since the inside wasn't just in x. So we have to multiply by the derivative of the inside, which is just the original fraction. So we have to multiply by 3x minus 1 squared all over x plus 1 to the 4th, all of that prime, the derivative. Excuse me. So now we're here. Now we have to take the derivative of this part now. In fact, let me actually make it clearer. Let me put brackets around it. So rewrite things. F prime of x equals x plus 1 to the 4th times 3x minus 1 squared times the derivative of this. Now this, since we have a fraction here, we're probably going to have to use the quotient rule. And the quotient rule again is if you have a over b, and you'll find this derivative, that's equal to a prime b minus ab prime all over b squared. In this case, a is 3x minus 1 squared, and b is x plus 1 to the 4th. So we just fit both of those into this formula down here, and we'll get its derivative. So doing that, we'll get a prime, that is the derivative of 3x minus 1 squared. So we're just going to write 3x minus 1 squared prime. Let me make those brackets match. There we go. Times b, so x plus 1 to the 4th, minus a, that is 3x minus 1 squared, times b prime, so the derivative of x plus 1 to the 4th. And this is all over b squared, so this is all, so underneath is x plus 1 to the 4th squared. So we've done one more step. Now we have one more to do. We've got this derivative here and this derivative here. Fortunately, that does look like it's going to be the end of the line for us. It's probably going to be the last derivative we have to do. Just kind of looks like a power rule and then a small chain rule after that. We can just roll those into one step. So this is now going to be f prime of x equals x plus 1. I messed that up. X plus 1 to the 4th all over 3x minus 1 squared times. So up here, this derivative now, well, we're going to use power rule. So we take this 2, move it out front. So this is now going to be 2 times 3x minus 1. And then 2 minus 1 is 1. So this is all raised to the first power. So we can just drop it. And then we do have to do chain rule. We have to multiply by the derivative of the inside, and the derivative of 3x is 3. Derivative of minus 1 is 0. So we multiply that by 3. So this is times x plus 1 to the fourth minus 3x minus 1 squared times this derivative now, x plus 1 to the fourth. Again, we could do power rule. We can take this 4 and move it out front to make 4 times x plus 1. So 4 minus 1 is 3, so this is now cubed. And we do chain rule again. We multiply by the derivative of the inside, and that is just going to be 1 since derivative of x is 1 and derivative of 1 is 0. So since this is just multiply by 1, I'm going to forget about it, and we are left with 4 times x plus 1 cubed. And then reiterating, this is all over x plus 1 to the fourth squared. That is just the same as x plus 1 to the eighth. And there we go. We have our full derivative now. That is pretty long. And I am not even going to attempt to simplify that. I'm sure you could, but for simplicity, we're going to leave it like that and just plug in 1 in for all of these x's now, so we can avoid a lot of work for ourselves. So f prime of 1 now is 1 plus 1 to the fourth all over 3 times 1 minus 1 squared times, this is now going to be 2 times 3 minus 1 times 3 times 1 plus 1 to the fourth minus 3 minus 1 squared times 4 times 1 plus 1 cubed all over 1 plus 1 to the eighth. All right, so doing this now, we get f prime of 1 equals, it's going to be 2 to the fourth all over 2 squared times, all right, so this is going to be 2 times 2 times 3. That is going to be 6 times 3, that's 18. Here we've got 2 to the fourth, which is going to be 2, 4, 8, 16. That's going to be 16 here. Minus, that's going to be 2 squared, which is 4. And then this here, this is 1. So 2 cubed is, so 2, 4, 8. So 2 cubed is 8. And 4 times 8 is 32. Yeah, 32. I got my powers of 2 memorized. And then on the bottom, we've got 2 to the eighth. That is going to be, so let's see, 2, 4, 8, 16, 32, 64, 128, 256. This is the eighth number, so this is going to be 256. That's a bad 2. Cool, so let's, one more step. Or not one more step, just the next step. We've still got stuff to do. 2 to the fourth, so 2 to the fourth divided by 2 squared, you just subtract the powers. So 4 minus 2 is 2 squared. So that's where this 2 is going to come from. This is all times 18. Ooh, okay, this is ugly. What we should do instead of just multiplying 18 and 16 is first rewriting this. So this 4 times 32, we can rewrite that as 8 times 16. So it basically took a 2 from the 32 and gave it to the 4. And now since we've got 2 16s in both of these terms, we can just take it out on the front. So we've got 16 times 18 minus 8. And this is all going to be over 256. Now this equals 4 times, this is 4, 2 squared. 4 times, all right, 16 times 10, so that's going to be 160 divided by 256. And this is now equal to, okay, normally when I make a mistake in these videos, I cut it and then just record an entirely new explanation, but this problem took so long and I made such a small mistake that I didn't really want to record the whole thing again. So in my explanation, what I did is for this step here, evaluating this, I evaluated that to be 18 instead of what it should be, which is 12. I've rewritten it here, and that completely changed the output of the problem. But now that it is 12, I am getting the right answer here, which is 256 over 256, which is just 1. So that is the right answer here. And I'm sorry if it was an abrupt cut that just happened there. I'm not really sure how I'm going to edit this together afterwards, but this is the right answer now, which I'm very happy I got.